Find the reaction force, Fr, in newtons. In this problem, a circular gate holds back a reservoir of water. The reservoir of water has a depth of 10 meters. The radius of the circular gate, r, equals 20 meters. And the gate has a total width, w, measuring 35 meters. The problem asks us to find the hydrostatic force, Fr, which is made up of a horizontal component, FRH, and a vertical component, FRV, where subscripts H and V identify the horizontal and vertical components respectively. The reaction force in the horizontal direction equals PC times A, where PC equals the pressure at the centroid of the gate wall from a horizontal perspective, and A represents the area of the gate from the horizontal perspective. We will further define the pressure term, PC, as rho g dc. We plug in the density of water, which is 999 kilograms per meter cubed. The gravitational acceleration, g, equals 9.81 meters per second squared. And since the gate appears like a rectangle from the horizontal perspective, dc is simply half the depth of water, d, which is half of 10 meters. This makes the centroidal pressure equal to 49,001 kilogram per meter second squared. The area of the gate, A, equals the depth of water, D, times the width of the gate, W. And after plugging in these known values, the area of the gate from the horizontal perspective equals 350 meters squared. Now we can solve for the horizontal reaction force on the gate, FRH, which equals 1.715 times 10 to the 7th kilogram meter per second squared. After applying a unit conversion and canceling out terms, the units of this force are in newtons. Next, we'll calculate the vertical component of the hydrostatic force, FRV. This force equals the pressure in the y direction times the area of the gate. This time, since we're dealing with a vertical force on a rounded surface, we can't use any shortcut methods such as how we use the centroidal pressure when computing the horizontal component. Therefore, we have to integrate the product Py and A to determine the vertical component of the hydrostatic force. In this equation, Py equals rho times g times the depth d. And we'll define the depth d equal to r times the sine of angle theta, where theta is defined as the angle inside the gate as shown. The area, A, equals the width times the depth, where, again, d equals r times the sine of angle theta. Now our equation for the vertical reaction force is rho g r squared w sine squared theta, and we'll integrate with respect to theta, where the limits of integration will span from 0 radians to theta. We can solve for the theta by taking the arc sine of the depth of water divided by the radius of the gate, since the structure of the gate forms a right triangle as shown. After plugging in variables d and r, we calculate theta equals pi over 6 radians, which is the same as 30 degrees. Now it's time to integrate sine squared theta d theta, which equals 1/2 theta minus 1/4 of sine 2 theta. After plugging in the limits of integration, pi over 6 and 0, our equation for the vertical component of the reaction force reduces to 0.04529 rho g r squared W. From before, we know the values of rho and g, and we also know the given radius and the width of the gate, r and w. This makes the force FRV equal to 6.214 times 10 to the 6 kilogram meter per second squared, which has the same units as newtons. Now that we know both the vertical and horizontal components of the reaction force, we can solve for the total reaction force, Fr, which equals 1.823 times 10 to the 7th newtons. When reviewing the possible solution, the correct answer is C.